Hello everyone, my name is Justin Houston, and today I'm going to be going over Transport 2, Exam 3 here, kind of carrying over from our second exam that I went over a couple weeks ago. And in doing so, we're going to have about 5 to 6 different parts of this. First part, defining the Lewis relationship. And in doing so, like I said, I'm deriving a few equations here. And what it's going to do is represent a wet bulb heat transfer experiment. So in doing so here, I'm going to be doing this on Windows OneNote. So bear with me. This is pretty much my first time using this. So it's a lot more easier compared to filming it on a whiteboard, in my opinion. So to start off here, I'm going to start off deriving the relationship between the null set number, null set over the Sherwood number, which is going to be equal to, they're both, starting with the null set number, you're going to have A times the Reynolds number, got to import that, A times the Reynolds number to some power B times the Prandtl number to some power C, and then that is also going to be over pretty much the same thing, A times the Reynolds to some power B, but the only thing different here is that it's going to be times the Schmidt number to some power, got to import that again, the Schmidt number to some power C. Oop. Alrighty, let me elongate this so you can get that on one row. And what I want to define here is for each of these variables. So we know that the get to the proper thing here. So we know that the null set number is going to be equal to the heat transfer coefficient times the diameter all over some, what am I trying to say? The mass transfer coefficient. We also know that the Sherwood number is going to be equal to thermal conductivity, which is Kc, times the diameter again all over diffusion coefficient DAB. So now that we have those, we can simplify this and say that the null set over the Sherwood is going to be equal to it's going to be equal to H times that diffusion coefficient DAB divided by mass transfer coefficient times, let me just add in the times there just so you're able to tell, times that Kc value, thermal conductivity. Let me see if I can put these into a that's more like it. Okay, I forgot how to do that for a second. And I'll do the same thing here for the first equation I made. Alright, it's already in math mode. So now that we have those two, I also wanted to define the Prandtl and Sherwood number, or Schmidt number. So in doing so, I'm going to do the same thing here. If I can get out of that. I don't know why it just went away. Alright, so defining the Prandtl number, we know that the Prandtl is equal to the kinematic viscosity. Actually, I think I can insert a symbol for this. Sorry, my computer's lagging a little bit. Kinetic viscosity all over alpha, which is the thermal diffusivity. And then, like I said, I also want to define the Schmidt number, which we know is equal to the kinematic viscosity again, divided by diffusion coefficient DAB. And then, so we know that we can combine the Prandtl over the Sherwood number. Well, that's what it is in the equation up there that I had given for us. And in getting that, when we combine the two, we get that diffusion coefficient DAB divided by alpha, which we can then simplify further. We know that this can then be equal to the diffusion coefficient times rho Cp, which is the density, rho times the heat capacity. Sorry, I forgot what it was for a second. And that is all going to be over. Let me make sure I have parentheses in there. That's going to be all over heat transfer coefficient. So now we have that. Put this all into mathematical form. I guess it already was. So now that we have that, we also know, just by looking at these two, we know that the A Reynolds to the B power, I don't know if I can put a strike through this. I don't think so. But we know that these cancel out, the A Reynolds to the B power on the numerator and the denominator, which leaves us with that Prandtl over the Schmidt number. And one other thing, we know that this relationship is also equal to 1 over the Lewis number. So now that we know that, well, I just realized that this formula is messed up a little bit. Did not want the Kc in the numerator. We want that down below with K, Kc. So what we now want to do is, we know in this experiment we have water coming in and out with air, and then we have it evaporating as well in that water, which is creating a heat transfer. So it's creating a moist air content. And in having that, we can then define each of these variables based off of known values for moist air. So in doing that, we can define, starting with, we can just say, we know that the mass transfer coefficient is, I don't know why that is capitalized. We'll just leave it. We know that that's a mass transfer coefficient. That's equal to 0.03 watts per meter Kelvin. We also know the density. There it is. Rho is equal to 1.2 kilograms per meter cubed. From there, let's make a new text box. We also have the heat capacity, which is equal to 1,000 joules per kilogram Kelvin. And we also know the diffusion coefficient DAB, which is 3e to the negative 3 meters squared per second. And now that we have that, when you plug that into this Prandtl-Sherwood Schmidt relationship, we know that that is approximately equal to 1, which lets us know that 1 over Lewis is also approximately equal to 1. And that we also know that this null set over Sherwood is going to be also equal to 1 over the Lewis, and that's all to the power c. I guess that's just the exponent value. And having that, we can then define this relationship further of the Prandtl-Schmidt. We can then take, I guess I'll just keep working off of this text box. We can then say that we can take DAB, the diffusion coefficient, all over K, and we know that that is going to be equal to rho Cp there, based off of this relationship. And then this leads us to know, kind of like an arrow there, that and we're forming this from the null set Sherwood as well. Took the DAB over K and then also the H over KC here. This allows us to know that this relationship is then going to be equal to 1 over that rho Cp, which then forms our, this is the Lewis relationship. And what is interesting about this is that we have the heat transfer coefficient all over the mass transfer coefficient. And this is basically telling us that that relationship is approximately 1, which is pretty fascinating. And that's basically what the Lewis relationship is here. That heat transfer over the mass transfer coefficient equaling to the 1 over, that is the kinematic volume, I believe. I might be mispronouncing that, but that is the relationship that we were looking for there. So this is going to be the second part of exam 3 for transport 2. Right now I'm going to be going over how to use the Lewis relationship to determine the relative humidity of a wet bulb experiment. So in doing so here, going to continue using OneNote. What we're going to do is define one energy balance. So starting with that, we're going to do, we're going to start with, actually I got to import these equations or symbols. So starting with lambda, which is the heat of vaporization, that's going to be times Kc, which we already know that is mass transfer coefficient, and this is going to be times C sub S. Hold on, let me see if I can elongate this. I'm not sure why there's this text box here. All right, there we go. Times Cs, which is the concentration of water at the surface, minus C, and if there's an infinity here, which is going to be the concentration of water far away from this surface. There it is. And then this is all going to be equal to lowercase h, which is the heat transfer coefficient times temperature far away from the surface, that is, and then temperature at the surface there. And let me elongate this a little more. So now that we have that, we also know that from that Lewis relationship, H over Kc, oh, not Hc, Kc is going to be equal to rho Cp, which is what I defined in the first video of this exam. So we can substitute this in by dividing the Kc here across. So you'd have the H over Kc there. We can then plug in rho Cp for that, which is the density times the heat capacity. So I'm going to copy and paste this just to save some time. Probably should have been doing that in the earlier videos too. But like I said, you divide that Kc over in the denominator of the heat transfer coefficient, and then we can substitute this rho Cp. Okay, so now that we have that, continue here. Let's see here. So yes, continuing on, we will still have basically the same formula, but a few things will change here. We can change this this concentration values to the partial pressure. I'll just use an uppercase P for partial pressure. That's going to be sub S, which is going to be the surface again of comma W, which is water, and then you'll have the same thing here, partial pressure far away from the surface of water as well. And then that's going to be all over, and I'll go outside here, all over, since it's an ideal gas, RT, and that's going to be the average temperature. You could also take the temperature of each area. Alright, that's much better. Of each part that you're talking about, so you could technically have the temperature of the surface and the temperature of water in the denominator of the respective units instead of T average, but we'll just use T average for now. And then we can change the rho Cp. We know this is going to be equal to the total pressure, and that is divided by, or we can just say that whole side is divided by, once again, RT average, that gas constant times the temperature average. Okay, that's not what I wanted. So anyways, now that we have that, I guess just ignore these text box. I don't know why it keeps changing it to that. So now that we have that RT average on both sides, and if we were to multiply across, those would cancel out. So once again, we'll have this lambda, the heat of vaporization, that is. But instead, like I said, the RT average cancels out, and that's going to be equal to, on the right hand side, you're going to have pretty much the same thing, except instead of the RT average in the denominator, well, actually you don't have anything in the denominator. You'll just have, with the total pressure, you're going to have that multiplied by the heat capacity. So that gives us that, and then this is going to basically allow us to know, and I'll explain this more in A3, or part A3 as well, but this pretty much allows us to know how to solve for the relative humidity, which we can get now as well. RH for relative humidity, that's going to be equal to that pressure of the, or that partial pressure of the water, and I guess I mixed these up. It should be, not that it really matters, but the partial pressure at the surface of the water, I'll just keep it the same. That's going to be divided by partial pressure of the saturated vapor of the water at T, at the temperature of the water as well. So yeah, that's the formula for And let me throw in some parentheses just so it's easier to understand. I know there's some commas that are kind of confusing. So yeah, once again, this is the partial pressure of the water at the surface divided by the saturation partial pressure of the water at a temperature of the water. So that is the end of that. And once again, the third video in the sequence will help us allow to understand how we actually get that relative humidity definition as well. So this is part 3 of the exam. I'm going to explain and continue on the relationship of the adiabatic saturation temperature and the wet bulb temperature. So just to get a better idea of how we're going to do this, just a representation, I guess, of the process we're looking at. So we have a elongated surface here that is insulated on both sides. And sorry, I'm trying to use my mouse to draw this so it's not the neatest. So this is the insulation here. And you have a layer of water running fluid through it with air as well. So you have the air coming in as well as it coming out. And both of those are going to have, let's type this, or actually I'll draw it, the mass flow rate of air coming in and out, and that's going to be at a temperature of T in. And then on the other end here, with this being the H2O, like I said, it's going to be coming out at that same mass flow rate, but you're going to have it as a temperature of the water outwards. So now that we have a general idea of that, we're going to want to write a steady state mass balance. And with doing so here, I will just start it right below it. Do an equation here. So to do that, we're going to start with the enthalpy inwards. And to do that, we're going to have this being equal to, I guess I should just have the equal sign here. I don't know if I can show like the mass flow rate, but we'll just say that M is the mass flow rate of air. Technically you should have a dot over it, but this is going to be equal to lambda, which is the heat of vaporization. Let's see, where is it? There it is, lambda, times the partial pressure of water, 1, times the molecular weight of water. That's going to be all over RT. So yeah, there's that. And then this is also going to be completely timed or multiplied by RT. And I guess I should go over real quick that this heat of vaporization, or heat of vaporization, I think it is in joules per kilogram of water. And to help get to these units, we want to include that molecular weight of the water, and then keep on moving. Since we have this meters cubed of kilograms, we want to add this next part here, which is the RT of the temperature in gas constant, and that's going to be completely divided by the total pressure times the average molecular weight. Yes, and then we're gonna add heat capacity times the temperature inlet, and that is going to be, I guess I should add one more parenthesis here and extend this. So that's going to be our enthalpy in equation. And then we're going to do the same thing but for enthalpy outwards. of that elongated tube. So this is going to be equal to, once again, you're going to have that mass flow rate of air coming in times that, and I'll just copy and paste this because it's practically the same thing, if it will let me. I don't know why it's being so difficult. So it's going to be the same thing, except right here you're going to have, you'll have that enthalpy of vaporization, or the heat of vaporization, partial pressure of water at location 2, which is the outward location, molecular weight of water, same thing here, but the only thing different here is that when we add that heat of vaporization, it's going to be times T2, or T outwards, and I guess you could say T1. I'll just change this to T1 so it's more consistent here. I don't know why it's being so... Alright, it's not letting me change that, so we'll just stick with that for now. So maybe if I extend this longer. Alright, there we go. Or not. It's just going to be difficult. Okay. So anyways, now that we have that, we can start canceling things out because we're going to set these two equations equal to each other. So what we're going to cancel out here is the mass flow rate, since it's on both sides. We can also cancel out the RTs, since they're in the numerator and denominator of each equation. Hold on, it's being difficult again. I don't know why it's not letting me type there. Alright, there we go. Alright, so in setting these equal to each other, like I said, you're going to have those canceling out. So we can then take out a few constants that we have, such as the lambda and the molecular weight, lambda enthalpy or heat of vaporization. So here I'll insert another equation. Like I said, we got lambda times, and I'll put this in parentheses, lambda times that molecular weight. And that's going to be divided by the, what can we take out as well? Oh, and I guess they converted it wrong. The average molecular weight should be in the denominator of the total pressure as well. It just moved it upwards. So just know that we're going to take those out, but they should both be in the denominator. So you're going to have that total pressure times that average molecular weight in the denominator, and that's what we're going to take out. And then we can have this all being multiplied by the difference of PW2, the partial pressure of water at location 2, minus partial pressure of water at location 1. And then that whole side is going to be equal to the difference, heat of vaporization times the difference of T2 minus T1. Alrighty, so continuing along with this, I realized I made a mistake here. It should be PW1 minus PW2 instead of vice versa. But what we're going to next want to do is here, continuing on, we want to pull from what we had found in A2, and that was we knew that heat of vaporization times molecular weight of water times the concentration of water at the surface minus the concentration of water at infinity, or away from the surface, that is. And that's going to be equal to the molecular weight of, actually no, it's equal to the heat capacity time, or rho CP. So let me put the rho in front of this. We found that from the correlation again of the Lewis relationship, and that's going to be T infinity minus T at the surface, temperature of water at the surface. And then we can continue this on. I'm just going to copy and paste this to save some time. Keeping the left side the same, we know that we can change this rho CP to total pressure, or yeah, P total times the average molecular weight, and that's going to be all over, put these in parentheses, divided by RT. There we go, perfect. And I was wrong, we do have to change this other side as well, the left-hand side. So we're going to want the partial pressure, saturation, or yeah, saturated partial pressure of water at TS minus partial pressure of water away from the surface, and we're going to want that whole thing divided by, hold on, it's not letting me extend this. We're going to want that whole equation divided by RT. And then you can notice that the RTs are going to cancel out there. So continuing on with that, I'll just copy and actually I don't want to copy and paste that. I want to copy and paste this. So we have that now. And like I said, the RTs are going to cancel out. And we still have, let's see if I can get rid of this. Nope. I'll just leave that, I guess. I think that's all I need. Actually, I forgot to carry down the heat capacity. So CP is still going to be in there. So obviously still have the heat capacity right here. So yeah, now that we have that, we can make this correlation that we were looking for at the beginning of this part. And that is that, where did I derive that? Oh, right here, from this equation here, when we set the enthalpy in and out equal to each other, we're going to notice that the surface temperature is going to be of the wet bulb is going to be equal to the saturation temperature of T2, as well as this saturation. Yeah, as I said, that's pretty much the correlation we're looking for. So now that we know that correlation, we can then rearrange this and pretty much flip what's ever in the parentheses at the ends there. So what we're going to have is we're going to have, on the left hand side, we're going to have that PW, the partial pressure water away from the surface, minus the partial pressure of the saturated water at the surface. And then we can then flip the right hand side, TS, temperature of water at the surface, and temperature away from the surface, which is infinity. So let me insert that real quick. You get the hint. It's not going to let me delete this parenthesis now, so it's supposed to be T infinity. But now that we have that, we can then solve for relative humidity. I mean, I already did solve for that, but we get the complete go-around reasoning for how we can actually solve it. So you have that partial pressure of the water at infinity, and that's going to be completely divided by that partial pressure of the saturated water at the hold on, that's not what I wanted. And that's all over the saturated water at infinity as well. So there is our equation for the relative humidity once again. And that concludes part A of this exam.